So in this video, I'd like to show you how to draw Lewis dot structures for compounds that violate the octet rule, where the central atom does not have an octet of electrons, 8 electrons around it. So the first case we will be talking about is the case where the central atom has less than octet around it. And the molecule that we will use to illustrate this point is boron trifluoride, BF3. So the first thing we're going to do is we're going to count the valence shell electrons. Boron is in group 3A, and it has 3 valence shell electrons. And fluorine is in group 7, so it has 7 valence shell electrons. And we have 3 electrons there, so it's 7 times 3 gives us 21, plus 3 gives us a total of 24 electrons in the valence shell. So next, we will draw the structure of this molecule. So we will pick boron as our central atom because boron is less electronegative than fluorine. Remember that when we look at the periodic table, the more the element is to the right and higher in the periodic table, the more electronegative it is. So boron goes in the center, and then it has 3 fluorines around it, and we will draw this as single bonds, like that. Okay, so now remember that each bond can be represented as 2 electrons. So we'll draw it like this. And then we will complete an octet around each fluorine by placing 3 more lone pairs on each fluorine. Like this. So now let's do our bookkeeping. So each fluorine has the 2 electrons that it shares with boron in a bond, and then 6 more electrons as lone pairs. So each fluorine has 8 electrons around it, a complete octet, and there are 3 of these, so it adds up to 24 valence shell electrons. So we accounted for all of our electrons, nothing else to put on the boron. But now let's check boron. Boron has only 6 electrons around it. Now the guidelines for drawing Lewis dot structure tells us that if the central atom does not have a complete octet, we have to draw multiple bonds. So something like this. However, this structure is not possible. And the reason for that is because fluorine is very electronegative, which means it holds on to its electrons very tight. It's kind of greedy that way. I call this a greedy atom. And it will just not donate its electron pair like this to form a multiple bond with boron. Therefore, boron has an incomplete octet. It has less than 8 electrons around it. But this is the reason why boron readily forms bonds with compounds that have lone pairs to donate. In other words, a typical example would be boron trifluoride and ammonia, because nitrogen has this lone pair. So now we have this new compound where we have nitrogen-boron bond, like this, and then this. And this compound is very stable, and the reason for that is because now boron has an octet. Remember that each bond represents 2 electrons. So now boron has 4 bonds around it, 8 electrons. Boron is very happy, and that's why this compound is very stable. Next, we will discuss the case where the central atom has more than 8 electrons around it. And to illustrate this point, we will use hexafluorous arsenate as an example. So first, let's count valence shell electrons. Arsenic is in group 5, so it has 5 electrons in its outer shell. Fluorine is in group 7, so 7 electrons in its outer shell, times 6, plus 1 for the charge, gives us a total of 48 valence electrons. So next, let's draw the structure of this compound. We will have arsenic in the center, because it's less electronegative than fluorine, and it would be surrounded by 6 fluorines, and we will draw single bonds like that. And we will put brackets around it to show the charge of this anion, -1. So now we will complete the octet for each fluorine. So each fluorine has 2 electrons that come from this bond, right? And then 6 more that we draw as lone pairs. Okay? And then we draw this for each fluorine. Like that. Okay, so now let's do our bookkeeping. Let's check if all of the electrons are accounted for. Fluorine has 2 electrons that come from the bond plus 6 electrons around it. So it's a total of 8. And there are 6 fluorines, so that adds up to 48 valence electrons. So we counted for all of them. So now let's see what is happening around arsenic. So arsenic has 6 bonds around it. Each bond contains 2 electrons, so that's a total of 12 electrons, which is a lot, way more than 8. And what's interesting here is, the question is, why is it that arsenic can form such a compound, whereas nitrogen, that is located in the same column and supposedly should behave the same way, cannot form something like this? The answer lies in the electronic configuration of each of them. So let's first look at arsenic. Arsenic has an atomic number of 33. So argon accounts for 18 of its electrons. But now remember that arsenic is in the 4th row of the periodic table, which means that it has d orbitals. So the outer shell of arsenic, 4s2, then we have 3d10. Its d orbital in the 3rd energy level is filled. And then we have 4p3. But more importantly, we still have the d orbital that is completely empty, has no electrons in it. So let's draw out the outer shell of arsenic. And I like to think of it as rooms that are in the house, with electrons as guests. So this would be 4s2. So it's one room, and it has 2 guests. So then we have another room, or I should say another floor, but now there are 3 rooms here. It's a p orbital, and it has 3 guests in it, and they are unpaired. And that is why compounds in this group typically form 3 bonds, right? Nitrogen, NH3 is ammonia, right? 3 bonds to hydrogen. But more importantly, we also have this D section of our house, which has 5 rooms, and they're all empty. That is why arsenic can accommodate 12 electrons. It has these spare bedrooms in its house. Now, if we look at the configuration of nitrogen, the picture is slightly different. The atomic number is 7. So nitrogen, helium accounts for 2 electrons here. And then we have 5 electrons in its outer shell. But nitrogen is in the 2nd row of the periodic table. And that means that nitrogen does not have d orbitals. Nitrogen does not have empty rooms in the house, and that's why it cannot accommodate the extra electrons.